Hi, welcome back. So let's start with control flow, where we'll see the for loop. There are other types of loops in Python, but this is the one that we will focus on. Now the for loop starts with the command for and then the variable that we will loop, and in this case t will take on the values 0, 1 and 2. Inside the for loop we have the commands that will be executed, so in this case we will print the values of t as t takes the value 0, 1 and 2, and outside the for loop we will print this string with the value of t. So inside the loop t had the values 0, 1, 2, and outside the loop it kept the last value 2. Now we can also represent a sequence of integers with the command range, and for the same sequence as the other example we say range 3, and range 3 will loop through 0, 1 and 2. So the last number, the one we used to call the command, so range 3, this 3, it's never reached. And here is an example where we use string formatting for the same purpose. Now the range command can have other parameters, can have starting variable, end variable, and the step. So in the earlier example we just used range end, which was 3. But that's because the default value for start is 0 and the default value for step is 1. But if you would like to have a range with a different starting value or a different step, this is how you would specify it. And keep in mind that range is exclusive of the value of end. So depending on the step, it will go up to n minus 1 with step 1. Okay, now let's talk about indentation, which we've seen in the examples. So in Python, indentation really represents logical structure. So if we have the same spacing in the block, it is the same logical block. And the standard is to use 4 white spaces. And this is the standard PEP8. However, in the Colab environment, where we'll be having our tutorial notebooks, we are using 2 white spaces. But it's still within standards, but the most often used is 4 spaces. Okay, let's talk about the if condition. An if condition is when you want to check for some conditions. So in this case, my variable tmax, if it is larger than 1, in this case, print that is larger than 1. So if I initiate my tmax variable with number 3, and if this condition is true, if tmax is larger than 1, which is the case, then it will print larger than 1. Now, we can also have an else statement that will execute if the first part is not true. If this part here is not evaluated to true, then what is here below, the else statement, will be executed. And this can be built with an elif or a sequence of elif commands, and then a catch-all else command where if all the previous ones fail, then this is the one that will execute. Okay, break and continue. Now these 2 commands are often used in loops. So let's say we have here a loop on t, and we want to, for some reason, exit the loop if t is larger or equal to 1. Okay, so with the break command, as t goes 0 and 1, but as it reaches the value of 1, then this if condition becomes true, and then we break the loop. So in this case, we break the for loop. On the other hand, let's say we don't want to break the loop, but we just want to skip some executions inside the loop, but still continuing the loop. In this case, we use the continue command. So if t equals 0, then we continue, meaning that we go back to the loop instead of continuing execution. So in this case, when t equals 0, we hit the if condition here, becomes true, continue, we go back to top, and then t equal 1. Now the if condition is no longer true, and so we print it, and so on. Okay, let's talk about discrete time integration. So we start from our membrane equation, and let's focus on the left side, on the derivative of Vt. Now, a derivative is given by a difference of, in this case, Vt at the value of t plus delta t, a small increment in t, with the value of Vt at the point t. So we take this difference, v plus delta t minus Vt, and we divide by the value of the small increment. Then we take the entire thing to the limits where dt delta t goes to 0. So if we don't take this limit, if we don't make delta t go to 0, then we'll have an approximation of the derivative, and this is the basis of the Euler method. Now, let me give you an example. On the left side, we have two plots. The synaptic input to our neuron and the time course of Vt responding to this synaptic input, which is just a sinusoidal input. So this plot was drawn with delta t of 1 millisecond. So in 1 millisecond, it means that our sinusoidal signal is not continuous, of course. It will be sampled at 1 millisecond intervals that are represented with these black points here. So let's see what happens if we use larger values of delta t. So now we've doubled delta t, and we see some differences, but we double again, and now something interesting happens. So we start seeing that our synaptic input does not really look sinusoidal. So the blue trace here does not really look the original continuous gray trace. And as a result, the response of our neuron is also very different from the gray line here that represents the original response with a small delta t. And of course, at one point, it really is very different. Our delta t is too large and it's not really representing the response of the neuron. Now, let's go back and use the initial delta t of 1 millisecond. And you may ask, but Marco, what happens if we use smaller delta t's? Will the simulation be much better? Well, you can use smaller delta t's. So here we have to half a millisecond, and you see that the differences, although you have already many more points in the sinusoidal input, the difference of the time course is not very large. And here we have again, and you see really a lot of points here on the input, but not much difference on the output. So what is going on here is that 1 millisecond for our simulation is about the right time for delta t. If we have much smaller values of delta t, your simulation will just run for longer, but qualitatively it will not be a big difference. Larger delta t intervals, yes, they affect and the simulation gets worse. Okay, so now that you've heard about this, it's time to implement it, and we go to exercise 4, where you will solve the discrete integration by hand and then implement it.